All right, so in these next two videos, we're going to look more closely at the interval on which a given series converges. And in this video, we're going to work through three examples illustrating how to find such intervals. And then in the next video, we'll state the main theorem that tells us more generally what an interval of convergence can look like. All right, so let's jump into question 3 that says, find the interval on which the series converges, then state the radius of convergence for the series. Now, we haven't discussed the radius of convergence yet, and we'll unpack this as we go through these examples. All right, now part A, we're looking at the sum of negative 1 to the n over n times x plus 2 to the n, and the sum starts at n equals 1. And when finding the interval on which a series converges, you always want to use the ratio test. Okay, so here a sub n is negative 1 to the n over n times x plus 2 to the n, and so a sub n plus 1 is negative 1 to the n plus 1 over n plus 1 times x plus 2 to the n plus 1. All right, so then to apply the ratio test, you want to start out by looking at the ratio of a sub n plus 1 to a sub n in absolute value. And so here I have a sub n plus 1 in orange. And then to divide it by a sub n, I'm going to multiply by the reciprocal of a sub n. You see that here in blue. And then we go ahead and simplify. So negative 1 to the n plus 1 over negative 1 to the n, that's negative 1. N over n plus 1. Since I'm anticipating taking a limit as n approaches infinity, I'm going to divide numerator and denominator by n. So this is 1 over 1 plus 1 over n. And then x plus 2 to the n plus 1 divided by x plus 2 to the n, that's just x plus 2. And I have this absolute value here, so I can drop the negative, pull out the 1 over 1 plus 1 over n, and note that the absolute value has to stay on the x plus 2, and that's because for certain values of x plus 2 is positive, and for other values of x plus 2 is negative. All right, so this is our simplified expression. And so now we can compute this quantity r, which is the limiting value of this ratio in absolute value, right? And so I'm taking the limit of this expression as n approaches infinity. And so since 1 over n goes to 0, we conclude that r is equal to x plus 2 in absolute value. All right, so now this leads us to 3 cases to consider. And I need to make a little bit of space here. Here are the 3 cases we are led to. Okay, the first case is when r, which again is x plus 2 in absolute value, is strictly less than 1. Here, the ratio test says that this series converges. And note that if x plus 2 in absolute value is strictly less than 1, that implies that x is strictly greater than negative 3 and strictly less than negative 1. Okay? Now, if r is strictly greater than 1, then the ratio test says that this series diverges. And this condition is equivalent to saying that x is strictly less than negative 3 or x is strictly greater than negative 1. Now, in the last case, this is when r is equal to 1, which occurs when x is either negative 3 or negative 1. Here, the ratio test is inconclusive. Okay, the ratio test does not tell us whether or not this series converges when x is negative 3 or when x is negative 1. Okay, so I've summarized these cases up on the number line. And at these 2 points, right, at negative 3 and negative 1, we have to check these separately. We've got to do some more work. All right, now when x is negative 3, note that x plus 2 is equal to negative 1. And so x plus 2 to the n is negative 1 to the n. And if I multiply that by negative 1 to the n, that just gives me negative 1 squared to the n. And that's just 1 to the n, which is, well, 1, right? So when x is negative 3, this series is equal to the harmonic series. And we know the harmonic series diverges, okay? So this series diverges when x is negative 3. Now when x is negative 1, here we have x plus 2 to equal positive 1. And so x plus 2 to the n is just 1. So now we're looking at the sum of negative 1 to the n over n. And this series converges by the alternating series test, right? B sub n here is 1 over n, and that's certainly a decreasing sequence, and it approaches 0 as n approaches infinity, and so this series converges by the alternating series test. All right, so now to summarize all that, I'll just copy this number line down here and fill in what we now know about these points at -3 and at -1. And so this interval in blue, right, which is the interval from -3 to -1, where we're not including this left end point, so an open circle on the number line, and note in interval notation, right, we use a parenthesis there, but we are including the right end point, so closed circle on the number line there, and here we use a bracket in the interval notation. Okay, so this is what we call the interval of convergence for the series. All right, so then what about the radius of convergence? Well, there, first I want to just point out that this series is centered at a equals -2. Okay, so x plus 2 to the n, that's our x minus a to the n. And note that when a is -2, x minus a is x plus 2. Okay, now where is a equals -2 on the number line? Well, note that it's right smack dab in the center, hence the name, of the interval of convergence. And what the radius of convergence measures, it measures the gap between the center of the interval of convergence and one of the endpoints. Okay, so here, that gap is equal to 1, right? The gap between -3 and -2 is 1, and the gap between -2 and -1 is 1. Now, in the next video, when we prove the main theorem on convergence intervals, okay, we're going to see that this gap from the center to the right endpoint and the gap from the center to the left endpoint are always the same. So it's never ambiguous what the radius of convergence is. Okay, so here the radius is equal to 1. All right, cool. So now let's go ahead and turn to part B. Fortunately, parts B and C are a little less drawn out. Okay, so for part B, we're looking at the sum of -1 to the n times 3x to the n over n factorial. Here the sum starts at n equals 0. So again, we're going to apply the ratio test. So here's a sub n. Here's a sub n plus 1. And so looking at this ratio, okay, I take a sub n plus 1, multiply it by the reciprocal of a sub n, and then simplify. And -1 to the n plus 1 divided by -1 to the n, that's just -1. N factorial over n plus 1 factorial. Well, we've seen this now a number of times. Get all this nice cancellation, so we just get a 1 over n plus 1. And then 3x to the n plus 1 over 3x to the n. That's just 3x. All right, so I have this absolute value here, so I can drop the negative, pull out the 3 over n plus 1, and the absolute value stays on the x. All right, so now to compute r, which is the limiting value, right, of this quantity, note that as n approaches infinity, 3 over n plus 1 approaches 0, right? And it's multiplying the absolute value of x. So in the limit, right, we're going to get 0 times the absolute value of x, and that is equal to 0. So here, the conclusion is that r is equal to 0, and that's true for all values of x. So the big takeaway here is that since r is in particular strictly less than 1 for all x, okay, the ratio test implies that this series converges for all x. Okay, so here I've shaded the interval of convergence, which is just the entire number line, right? So everything gets shaded in blue. And in interval notation, right, the interval of convergence is just -infinity to infinity. Okay, now what about the radius of convergence? Well, here note that the center of this series is at a equals 0, right? So for our x minus a to the n, here we just have powers of x, right? We just have this x to the n, so a is 0. So there's the center of the series. And as we said in part A, right, the radius of convergence measures the gap between the center of the interval of convergence and one of the endpoints. Okay, but since, right, we're talking about the entire number line here, that gap is infinite. And so here the radius of convergence is infinity. All right. And so now let's go ahead and look at the last part. This is part C. Okay, so we're looking at the sum of n factorial times x minus 3 to the n, and n starts here at 0. Okay, so again, we'll apply the ratio test. A sub n is here, a sub n plus 1 is here. So looking at this ratio, okay, I have n plus 1 factorial times x minus 3 to the n plus 1 over n factorial times x minus 3 to the n in absolute value. Okay, so we can simplify n plus 1 factorial over n factorial. Okay, we're just going to get an n plus 1 left over, because again, you get a whole bunch of nice cancellation. For x minus 3 to the n plus 1 over x minus 3 to the n, there we just get an x minus 3. And then here in the next step, I'm just pulling out the n plus 1. So we have n plus 1 times x minus 3 in absolute value. All right, so now when I go to compute r, which is the limiting value of this expression, got to be a little bit careful here, okay? So first note that if x is equal to 3, well, x minus 3 is equal to 0. So in that case, I'm going to have 0 times n plus 1, and that is equal to 0. So then if I take the limit as n approaches infinity of 0, well, I'm just going to get 0. Okay, so r is equal to 0 when x is equal to 3. Now, on the other hand, if x is any number other than 3, okay, well now x minus 3 in absolute value is going to be a positive number. And see, it's multiplying n plus 1, which is blowing up to infinity. All right, so this product then is going to approach infinity as n approaches infinity. All right, so here we conclude that r is equal to infinity when x is not equal to 3. All right, so the ratio test implies that when x is equal to 3, since r is 0, well, in particular, it's strictly less than 1, so this series converges. Now, when x is not 3, r is infinity, so in particular, it's strictly greater than 1, and so this series diverges. And I've illustrated that here on the number line. All right, so now for our interval of convergence, well, we really just get a single point in this case. So I've written the singleton in set notation. So this is the set of all x such that x is equal to 3, which is really just describing this one single point. Okay, now what is the radius of convergence? Well, note this series is centered at a equals 3. And since I only have convergence when x is equal to 3, right, the gap between the center and one of the endpoints is 0 in this case. All right, so that's going to do it for these 3 examples. In the next video, we'll state the more general theorem, and I will see you there. Thanks.